December 16, 1944, the Battle of the Bulge. Obergefreiter Hans Müller crouched in his foxhole in the Ardennes forest, listening to the whistle of incoming American artillery. After 3 years on the Eastern Front, he knew the sound of death approaching. He pressed his face into the frozen earth and waited for shells to impact somewhere nearby. They never did. Instead, the shells exploded directly above his position with surgical precision, raining deadly fragments down on German troops who had no cover from an aerial burst. The detonation came at exactly the right altitude to maximize casualties while minimizing crater damage that might provide shelter. Müller had never experienced anything like it. German artillery shells exploded on impact or with timed fuses that were notoriously unreliable. These American shells seemed to possess an intelligence of their own, knowing exactly when to detonate for maximum lethality. What Müller couldn't know was that he was experiencing the world's first proximity-fused artillery shell, a weapon so revolutionary that Germany's finest scientists couldn't even understand how it worked. For 3 years, German engineers had captured proximity-fused shells, dissected them component by component, and stared in bewilderment at technology that seemed to violate basic physics. 50 separate research projects had attempted to comprehend American innovation. All 50 had concluded the same thing. The weapon was impossible. The shells contained electronic circuits that somehow survived artillery acceleration forces that should have destroyed any known vacuum tube. They housed miniaturized radar systems that operated on principles German scientists couldn't identify. Most impossibly, they were being mass-produced by the hundreds of thousands at costs that made no economic sense. This is the story of the proximity fuse, the American weapon that German scientists couldn't understand. How American engineers created technology that Nazi researchers declared theoretically impossible, and how a shell that seemed like magic became the innovation that revealed the true gap between American and German science. The impossibility began 3 years earlier, when American scientists attempted something that violated every known principle of wartime engineering. January 1941. The National Defense Research Committee faced a problem that had plagued artillery since the invention of gunpowder: how to make shells explode at exactly the right moment to maximize their effectiveness against aircraft and infantry. Traditional artillery shells used impact fuses that exploded on contact or timed fuses that exploded after a predetermined delay. Both methods were unreliable and ineffective. Impact fuses were useless against aircraft, while timed fuses required gunners to calculate precise flight times under battlefield conditions, calculations that were usually wrong. What the military needed was a shell that could detect its target and explode at the optimal distance automatically. The concept seemed simple enough, but the engineering requirements appeared impossible by 1941 standards. The proximity fuse would need to contain a miniaturized radar transmitter and receiver small enough to fit inside an artillery shell, electronic circuits capable of surviving artillery acceleration forces exceeding 20,000 Gs, a reliable power source that could function after extreme shock, and manufacturing techniques that could mass-produce precision electronics at artillery shell prices. Every requirement violated existing technological limitations. Radar equipment in 1941 filled entire rooms and required massive power supplies. Electronic circuits were fragile devices that failed under minor vibrations. Mass production of precision electronics existed only in theory. German scientists, studying the same problem for the Luftwaffe, had concluded that proximity fuses were theoretically interesting, but practically impossible with available technology. The engineering challenges were simply too great for wartime solutions. American scientists decided to ignore the impossibility and solve the problems anyway. September 1940. The Proximity Fuse project began at Johns Hopkins University's Applied Physics Laboratory under the direction of Dr. Merle Tuve. The team included some of America's most innovative engineers, but innovation alone couldn't overcome the fundamental physics problems they faced. The primary challenge was creating a radar system small enough to fit inside an artillery shell, yet sensitive enough to detect aircraft at precisely the right distance. Existing radar technology used wavelengths measured in meters and required enormous antennas. Artillery shells measured their interior space in inches. The solution required abandoning conventional radar principles entirely. American engineers developed a new approach using ultra-high-frequency radio waves that could operate with antennas small enough to fit inside shell nose cones. The technology didn't exist anywhere else in the world, but miniaturized radar was only the beginning of the challenges. Electronic circuits in 1941 used vacuum tubes, fragile glass devices that shattered under mild shock. Artillery shells experienced acceleration forces that would pulverize conventional electronics instantly. The shells needed circuits that could survive forces equivalent to dropping a radio from a 10-story building while simultaneously operating with precision that exceeded laboratory standards. American engineers solved this problem by developing ruggedized vacuum tubes specifically designed for artillery use. The tubes used innovative construction techniques that German electronics couldn't duplicate, techniques so advanced that German scientists would later conclude they were physically impossible. March 1942. The first proximity-fused shells underwent testing at the Naval Proving Ground in Dahlgren, Virginia. The results exceeded every expectation and violated German assumptions about what American industry could accomplish. The shells consistently exploded within lethal range of their targets, achieving accuracy rates that made traditional anti-aircraft guns suddenly effective against high-speed aircraft. More incredibly, the manufacturing costs were low enough to justify using proximity fuses on ordinary artillery shells rather than specialized anti-aircraft rounds. German intelligence, monitoring American weapons development through captured equipment and interrogated prisoners, initially dismissed reports about proximity fuses as propaganda. The described capabilities were too advanced for American technology, according to German scientific assessment. American industry was considered competent at mass production, but inferior to German precision engineering. The idea that Americans had solved electronics problems that challenged German science seemed preposterous to researchers who considered themselves the world's technological leaders. This assumption would prove to be Germany's greatest scientific miscalculation of the war. August 1943. German forces first encountered proximity-fused shells during Allied bombing raids over Europe. Luftwaffe pilots reported anti-aircraft bursts that exploded with uncanny accuracy, appearing to track aircraft movements and detonate at optimal distances regardless of evasive maneuvers. Initial German analysis concluded that Americans had developed some form of remote-controlled detonation system, perhaps radio signals from ground operators who could observe aircraft and trigger explosions manually. The idea of autonomous shells that could detect targets independently seemed too advanced for American capabilities. But when German engineers examined captured proximity fuses, they discovered something that challenged their understanding of physics and electronics. The fuse components were impossibly small, yet remarkably sophisticated. Miniaturized circuits operated on principles that German scientists couldn't identify. Vacuum tubes survived shock forces that should have destroyed them instantly. Most puzzling, the entire system was manufactured with precision that exceeded German laboratory standards, yet was obviously mass-produced at industrial scales. Dr. Heinrich Müller, heading German proximity fuse research, submitted his initial assessment to the Reich Research Council. American fuse technology appears to violate established principles of electronics and manufacturing. Components exhibit capabilities that our theory suggests should be impossible. Recommend immediate investigation into American industrial methods. October 1943. The German proximity fuse project officially began with a directive from Adolf Hitler himself. German science must duplicate and improve upon enemy fuse technology within 6 months. 50 research teams across the Reich received captured American shells and orders to reverse engineer the proximity fuse immediately. The teams included Germany's most accomplished scientists, engineers from major industrial corporations, and specialists from universities that had pioneered electronics research. If anyone could understand American technology, these were the men who could do it. Within weeks, every team reached the same conclusion. The American proximity fuse was impossible according to known scientific principles. The electronic circuits used vacuum tubes that were somehow immune to shock forces that destroyed German equivalents. The radar systems operated on wavelengths that required antenna configurations that couldn't fit inside artillery shells. The manufacturing techniques achieved precision at costs that violated basic economics of electronics production. Dr. Werner Osenberg, coordinating German research efforts, reported to Armaments Minister Albert Speer, "American fuse technology challenges fundamental assumptions about electronics, manufacturing, and physics. Our teams can identify individual components, but cannot understand how they function as a system. The engineering principles appear to be beyond current German knowledge." December 1943. German teams had spent 3 months dissecting American proximity fuses component by component, creating detailed diagrams of every circuit and measuring every dimension. They understood what the Americans had built, but remained completely mystified about how it worked. The vacuum tubes were the greatest puzzle. German electronics used carefully calibrated tubes that required precise operating conditions and protection from vibration. American tubes somehow functioned reliably after being subjected to artillery forces that should have rendered them inoperable. German scientists tested their own tubes under similar conditions and achieved 100% failure rates. American tubes not only survived the shock, but continued operating with accuracy that exceeded laboratory standards. The materials and construction techniques were completely unknown to German science. Dr. Hans Hollmann, Germany's leading radar expert, concluded that American proximity fuses used scientific principles that German research had not yet discovered. "We are examining technology that appears to be decades ahead of our current understanding," he reported. "The Americans have achieved breakthroughs that we cannot duplicate or even comprehend." The admission was devastating to German scientific pride and strategic planning. March 1944. After 6 months of intensive research, German proximity fuse teams had achieved exactly nothing. They could describe American technology in precise detail, but couldn't explain how it functioned or duplicate its capabilities. German industrial leaders suggested that the problem might be manufacturing rather than scientific. Perhaps Americans had developed production techniques that allowed them to build electronics at scales and costs that German industry couldn't match. Investigation revealed that American proximity fuse production exceeded 100,000 shells per month, a manufacturing rate that German industry declared impossible for precision electronics. The Americans were somehow mass-producing advanced technology at costs lower than German mass production of simple artillery shells. The manufacturing mystery deepened when German intelligence determined that American proximity fuse production was dispersed across multiple factories using workers with minimal technical training. German electronics required skilled technicians and laboratory conditions. Americans were building advanced electronics with assembly line workers in industrial settings. Hermann Goering, reviewing German progress reports, declared the entire American program a scientific impossibility masquerading as military technology. He ordered German research to continue, but privately concluded that American claims about proximity fuse capabilities were propaganda designed to demoralize German forces. June 1944. D-Day provided German forces with their first large-scale exposure to American proximity-fused artillery. The results shattered every assumption about American technological capabilities. Allied naval bombardment used proximity fuses that exploded with devastating precision above German defensive positions. Artillery shells that should have buried themselves harmlessly in beach sand instead detonated in midair, multiplying their effectiveness against personnel and equipment. German defenders reported that American artillery seemed to possess supernatural accuracy. Shells exploded at optimal heights regardless of weather conditions, visibility, or defensive countermeasures. Traditional protection against artillery, trenches, bunkers, dispersed formations, proved inadequate against weapons that exploded above rather than beside their targets. General Erwin Rommel, commanding German coastal defenses, submitted an urgent request for proximity-fused technology. Enemy artillery capabilities exceed all previous experience. German forces require equivalent weapons immediately to maintain defensive effectiveness. The request was forwarded to proximity-fused research teams who were still struggling to understand how American shells functioned. September 1944. German research entered its final phase with a comprehensive effort involving every available scientific resource. Universities, industrial laboratories, and military research facilities combined their expertise in one last attempt to comprehend American proximity-fused technology. The collaborative effort produced the most detailed analysis of American electronics ever conducted by German science. Teams identified every component, measured every dimension, and tested every circuit. They created perfect technical drawings and comprehensive parts lists. But understanding remained as elusive as ever. Dr. Gustav Hertz, Nobel Prize winner in physics, led the final assessment. American proximity fuse represents scientific achievement that challenges our fundamental understanding of electronics and manufacturing. The technology incorporates principles that German science has not yet discovered and manufacturing techniques that German industry cannot duplicate. The conclusion was unprecedented in German scientific history. American technology was so advanced that German science couldn't understand it. November 1944. The Battle of the Bulge demonstrated the full impact of German failure to understand American proximity fuse technology. German artillery, using traditional impact and timed fuses, proved markedly inferior to American guns equipped with proximity fuses. American artillery achieved devastating accuracy against German infantry formations, vehicle concentrations, and defensive positions. German artillery, despite numerical advantages in some sectors, couldn't match the effectiveness of American proximity-fused shells. Most frustrating for German commanders, captured American shells continued to reveal technology that German scientists declared theoretically impossible. After 18 months of intensive research, German understanding of proximity-fused principles hadn't advanced beyond initial bewilderment. Field Marshal Walter Model reported to Berlin, American artillery superiority stems from fused technology that German science cannot duplicate or understand. Enemy capabilities exceed German theoretical predictions by margins that suggest fundamental gaps in our scientific knowledge. January 1945. German proximity fuse research officially concluded with a final report that acknowledged complete failure to understand American technology. 50 research teams, hundreds of scientists, and millions of Reich marks had produced no usable results. The final assessment, classified at the highest levels, concluded that American scientific capabilities exceeded German understanding by decades rather than years. Proximity fuse technology represented an innovation gap so wide that German science couldn't bridge it within any reasonable time frame. Dr. Osenberg's concluding report stated, American proximity fuse demonstrates scientific and industrial capabilities that German research cannot currently explain or duplicate. The technology appears to incorporate principles unknown to European science and manufacturing techniques that exceed German industrial capacity. For a scientific establishment that considered itself the world's most advanced, the admission represented a devastating blow to German technological confidence. May 1945. Germany's surrender ended the proximity-fused research program, but post-war investigation revealed the full scope of German failure to understand American innovation. American proximity fuses had used scientific principles that German researchers never identified: innovative vacuum tube construction, ultra-high-frequency radar techniques, mass production methods that achieved precision at unprecedented scales, and electronic circuit designs that combined reliability with miniaturization. More significantly, American success had resulted from collaborative approaches that German science couldn't duplicate. Industrial engineers, university researchers, and military specialists had worked together in ways that challenged German assumptions about scientific organization and technological development. The proximity fuse represented more than individual innovation. It demonstrated systematic American advantages in research coordination, industrial integration, and technological application that German science hadn't recognized or understood. German post-war analysis concluded that American scientific capabilities in 1941 had already exceeded German levels by margins that made technological competition futile. The proximity fuse wasn't just a superior weapon, it was proof that American science had achieved breakthroughs that German research couldn't comprehend. The weapon they couldn't understand had revealed a scientific gap that German pride had prevented them from acknowledging until defeat made denial impossible. In the end, Hitler's scientists had failed 50 times, not because they lacked intelligence or resources, but because they faced technology so advanced that failure was inevitable. American engineers had solved problems that German science didn't know existed, using principles that German research hadn't discovered. The proximity fuse became a symbol of American technological supremacy, precisely because it seemed impossible to German experts who considered themselves the world's scientific leaders. When German science declared something impossible, American engineering made it work anyway. It was the ultimate demonstration that innovation could overcome tradition, that practical problem-solving could exceed theoretical knowledge, and that underestimating American capabilities was Germany's greatest scientific mistake of the war. The weapon they couldn't understand had helped win the war by revealing that American science was already fighting a conflict that German research didn't know had begun.